So last class we finished your synchronous generator, right? And synchronous generator and synchronous motor, there is not much difference. The constructional features are same almost. And only the operational principles are little different. So we'll talk about that only operational aspects of synchronous motor. Okay. So the synchronous motor is very useful when it is operated under no load condition rather in the loading condition, because under loading condition it sometimes happens that when the load is more, it cannot take the load much as the load torque becomes greater than the generated torque. The motor then becomes standstill. Okay? It cannot bear, so because it has to operate at the synchronous speed. If it is other than the synchronous speed, it has to halt its operation. Okay, so we'll see the synchronous motor is actually always it operates under synchronous speed, and as we know the synchronous speed same means the frequency of the applied voltage remains constant and the number of poles of the machine, right? Also it remains same. So the speed of the synchronous motor is independent of the load as long as the load is within the capability of the motor. That means your load torque is within the generated torque, maximum generated torque, right? So it should not exceed the maximum torque generated by the motor. Okay. So for this reason, a synchronous motor is not inherently self-starting. So it cannot self-start. Because why it will be not self-starting, I will explain you, because there is some issues. So it will unable to start with it. So as soon as you connect the supply to the synchronous motor, it cannot start. Unless we take it to the speed near to the synchronous speed, it cannot. So therefore there are certain arrangements are made. The first arrangement is we have to take the motor speed somehow using the prime mover to the near to the synchronous speed, then where it achieves the synchronous speed and rotates at the synchronous speed. Then you can remove the prime mover. As we have seen in the your synchronous generator in the lab also can be operated as the synchronous motor if we can take the speed of the motor to the synchronous speed and leave the prime mover open, right? So because of its constant speed torque characteristic, it has very useful application in the timing devices like clocks, right? And also because it operates always in the synchronous speed, and also it can be used under no load condition for improving the power factor of the load. When the load is actually operating under inductive load, lagging power factor, highly inductive load we can say, under that condition it provides a capacitive effect when it operates as a leading power factor, right? So therefore it compensates the lagging power factor and it normalizes the power factor towards the unity, and therefore sometimes it is known as the synchronous condenser. Okay. Mostly it is used as synchronous condenser in the high voltage network. So, but nowadays because of the advent of the variable capacitance, or we can say the power electronics based capacitance, that is thyristor based capacitance. So gradually the use of this condenser is obsolete nowadays. It is not used in the power system. Okay, so then we'll see construction and operation of the synchronous motor. As I told, the constructional feature is same because the rotor, on the rotor side we have the field, and on the stator we have the armature, right? And the stator side, that as you can see here the figure, on the stator side we have the armature winding. We can see these slots here. They're actually they're containing the armature windings, right? And how these armature windings are accommodated, there are three-phase winding, right? Because we are giving the three-phase supply to the motor. So the three-phase windings are accommodated in a distributed manner. That means the axis of each phase or you can say axis of the each phase MMF is actually away 120 degree from each other, right? So in the rotor we can see we have a DC supply given to excite the field coil, and it creates the north and south pole. Similarly in the starter side, when we give the three-phase supply, it also produces the number of poles. For each phase there are number of poles. So it depends upon the design. It can be 4 pole for phase, sometimes 2 pole for phase. 2 pole is minimum, of course. It can produce 6 pole per phase, right? It depends upon the design. So but 2 pole is minimum, where in each phase it produces 2 pole. 2 pole means one north pole, one south pole. It is the minimum requirement, right? So here we can say the three-phase supply is given to the starter winding, right? And here the rotor is salient in feature, salient structure. It is not the cylindrical structure, right? And here we can see the starter winding, how it is actually wound. So we can see here three-phase winding. We can see phase 1, let us say S1 and F1. S1 indicates the starting end, and the F1 indicates the finishing end. F indicates finishing end, S indicates the starting end. So S1 and F1, it will be comprised of one phase. We can see here. It starts from here and it goes up to here, then again it comes to here, and this ends here, right? So this is, we can say, let us say phase A. So that is phase A, which is consisting of 1 and 1 dash, the terminals, right? End of the winding. Similarly, let us say S2, it starts from here, S2, right? And again it goes here and then it ends here, right? So here it is S2 and F2. So this is phase B, right? Phase B winding. Similarly, each phase, now this is S3 and F5, sorry, S3 and F3, they are actually called the phase C. Okay. So now we can see the MMF axis or flux directions. If let us say the flux is marked for phase A as this, let us say for phase A I can mark flux is from 1 to 1 dash. Let us say this is your phi A, right? Okay. And similarly, or you can say phi 1, it is better to write phi 1, it is concerning to phase A. And similarly, if I write phi 2, then phi 2 will be in the direction of F2 to, in this direction it will be 2 to 2 dash, so it will be phi 2, right? And similarly phi 3 will be here in this direction, it is phi 3. Okay, now we can see the distribution. Because of this distributed winding, the generation of flux is in the direction which is away 120 degree from each other, right? We can see it. This is the phase sequence is phi 1, phi 2, phi 3, or I can say phi A, phi B, phi C, right? Whatever, the notation may change according to our requirement. Now if we see if we derive the magnitude of the flux produced, let us see. So we'll consider the current first in the winding. So we have three-phase current we are injecting to the winding, armature winding, right? So I1 will be Im sin omega t, and I2 will be Im sin omega t minus 120 degree apart from I1. Similarly, I3 will be Im sin omega t minus 240, or I can say omega t plus 120, right? Now based on this, these are the current waveforms what we are injecting to the armature circuit, right? Now let us find the flux, magnitude of the flux produced at different instances. That will give us a clear picture. Let us say I will consider the instance where omega t equal to 0. Okay, at omega t equal to 0 I want to find the flux in the armature, right? So then what will be the values of I1, I2, I3 at omega t equal to 0? I1 will be of course 0 because it is Im sin omega t, So at omega t equal to 0, it will be 0. Similarly, I2 is Im sine of omega t minus 120. If I will put omega t equal to 0, it will be minus of 0.866 Im, right? Similarly, I3 will be 0.866 Im. Okay. So now, if I calculate the flux and current, their nature will be same almost, because there is no. So if we'll say phi 1 will become 0, phi 2 will be here minus of 0.866 Im, phi 3 is 0.866 Im, right? Now let me plot the magnitude of all these fluxes here. So we can see here, these are the winding structure. It is given S1, F1, S2, F2, S3, F3, right? Now the flux I want to plot. So phi 1 is 0, right? So phi 1 is 0, therefore no phi 1 is shown here. And phi 2 should be from 2 dash to 2, it should be in this direction. This is phi 2, but because it is minus of 0.866 phi m, so it will be plotted in the opposite direction. So phi 2 will be opposite direction, it will be equal to minus of 0.866 phi m, right? And phi 3 is, of course, phi 3 will be in the same direction, right? From 3 dash to 3, so it will be 0.866 phi m, right? So now phi 2, phi 3 we have, phi 1 equal to 0. Now what will be the resultant flux? It will be here, right? So resultant flux phi r1 is shown here. It is just the vector sum of phi 2 and phi 3, right? So vector sum, if we will find of phi 2 and phi 3, it will give the magnitude of 1.5 phi m. Okay, so that is 3 by 2 phi m. Okay, so this is the resultant flux at omega t equal to 0, at the instant when omega t equal to 0, right? And the direction we are seeing here. Now we'll move to another instant. So that instant is, let us say, omega t equal to 60 degree. Okay, so at omega t equal to 60 degree, your current values will become this. I1 will become 0.866 Im, I2 will become minus 0.866 Im. Just substitute in the current expression omega t equal to 60, right? You will find all these expressions, and your I3 will become 0, right? Now, if I'll plot these fluxes, so flux will become, phi 1 will become 0.866 Im, and phi 2 will become minus 0.866 Im, and phi 3 will be 0, right? Now if I'll plot this phi 1, phi 2, phi 3 is 0, so phi 1, phi 2 if I'll plot, now the resultant flux will be here. Okay, so at the instant omega t equal to 60 degree, what we are observing is that your resultant flux is moving, like it is moving another 60 degree, right? Or 30 degree, whatever. Okay, 60 degree it is moving, right? So we can say that phi r2, the magnitude remains same, that is 1.5 phi m, but it is rotating as your current is moving ahead, right? So current instant that is moving ahead, your flux is also, the flux direction is also, net flux direction is also rotating. Then we will take the third instant where omega t equal to 120 degree. Okay, under that condition also, if we'll find the expression for current, I1 equal to 0.866 Im, I2 becomes 0, and I3 will be minus 0.866 Im. Similarly, if we'll plot phi 1, phi 2, phi m, so phi 1 will be same, right, 866 phi m, and phi 2 will be 0, phi 3 will be minus 0.866 phi m, right? Now if I'll plot these fluxes and find the net flux phi r3, now it is rotated about an angle of 60 degree, another 60 degree, right? So therefore we can say that as the time passes, omega t is increasing gradually, your flux is also rotating in the direction, right, in the moving. So that means it creates a rotating flux, and this is how, I hope in the beginning Professor Siva Subramanian has taught you, that a three-phase distributed winding, when it is supplied with a three-phase supply, it will produce a flux that is rotating at the synchronous speed. Okay, and that is what we are observing here. The flux produced by this three-phase distributed winding is rotating at the same speed of omega. We are seeing here, right? As omega t is becoming 60 degree, it is moving 60 degree ahead, right? So that means it is rotating at the synchronous speed. So that synchronous speed we can find from this expression. Already we derived this expression, that is 120 F by P. P is the number of poles per phase. So F is your frequency of the supply, right? And P is your number of poles per phase. Okay, per phase, whatever poles we have. So this Ns is your speed in RPM. Okay, so this is how we saw that so that means in a synchronous motor, the three-phase winding, distributed three-phase winding on the starter, when it is supplied with a three-phase supply, it will create a rotating flux that is rotating at the synchronous speed. The flux magnitude is 3/2πm, that is 1.55 m. Okay. Up to this, I hope everything is clear. Now the question is, what will happen when we start a synchronous motor? So this flux is rotating at a synchronous speed in the starter, and we have another rotor circuit where the flux is unidirectional, and under starting condition it is zero speed, right? N is 0. So the rotor is not rotating. Now you gave a DC supply. So what will happen? As you gave a DC supply, here you can see the figure very clearly. Here. So here we have a flux, that is resultant flux, which is rotating at omega, speed of omega, on the periphery of the armature, right? And now we have another field which is actually here, right? It is creating N and S, and because of this flux also it will have N and S poles, right? This flux is produced because of some N and pole creation in the starter circuit, right? Starter side. So in the starter side we have a pole, we have a magnet which is having north and south pole which is rotating at synchronous speed, and we have another magnet on the rotor which is on the starting condition. Now what will happen to your machine? Will it start rotating? Any common idea? Will it start rotating? One magnet is rotating on the starter, right? That is at synchronous speed, and other magnet is on the rotor which is not rotating at the static. Now will it start rotating? No. Why it will not start? Because when north pole will come here, it may attract the south pole, right? Okay, then it may start rotating. It will start rotating in fact, but again it will repel back. Why? When the north pole will come here, the south pole will become attracted to this. It will start rotating, and as soon as it start rotating, immediately the south pole comes, because the rotor speed is very small, right, as compared to the rotating magnetic field on the starter. So the south pole will come here again, and again it will repel. So that means one time it will attract, other time it will repel back. Attract, repel back. That means it will not, it will just oscillate, it cannot start. So therefore your synchronous motor is not self-starting. It cannot start. So then what to do for the starting? One way is, I told in the beginning, one way is we have to give a starting torque such that it will go near to the synchronous speed. As it will go near to the synchronous speed, then it will lock. The rotor and starter fields will lock each other and it will start rotating at the synchronous speed. Up to the locking point we have to take to the rotor speed. And this is the one way. And another way of approaching to this is that we need to put the squirrel cage or we can say the squirrel cage compensating windings on the rotor surface. So around the rotor, if we'll put the squirrel cage bars, that means the conductors around the rotor surface, which will be sorted in both the side, right? And as soon as there is the field is created, it around the squirrel cage, it will start creating another rotating flux in that compensating winding, and that will actually help in rotating the rotor. Okay, we'll see how it is. Okay. So now we saw up to this. Now starting and the impact of the load variation we'll see, right? So we can say on the rotor surface we'll put the damper winding or the compensating winding here. These are the windings I put on the surface of the rotor. Okay. So now these conductors put on the surface of the rotor, that will form the squirrel cage like this. You can see here, these bars will be on the rotor surface. Okay, and they will be sorted both the ends, at the front end and the back end, they are sorted through this. And this looks like exactly a cage, squirrel cage. Okay. Okay. So the benefit of this is, as soon as it is put, then if it is designed like this, then another flux will be created which is rotate on the rotor surface itself in the synchronous speed. Okay, and that will try to catch the starter poles which is rotating at the synchronous speed, right? So then gradually it will start moving. When it will start rotating, then finally it will lock at the synchronous speed. Okay. And this is the three-phase damper winding, we can say. We can see here how it is connected to the rotor circuit. We can see here through the slip rings it is connected, and here we have variable resistance is given just in order to adjust the torque here. And this is your main field circuit, okay, where we are giving the DC supply. To this damper circuit we need not to give any kind of supply. It will be automatically, the voltage will be induced in it and the current will flow and it will produce its own flux because it is sorted at both the ends, right? So therefore the current will start flowing in the conductor and automatically the flux will produce and it will rotate. The flux will rotate, right? So this is the principle of induction motor, okay, and this principle is being employed here just to start the synchronous motor, and it will achieve this up to the synchronous speed, right? We'll see in the synchronous induction motor class also. So now let us see the equivalent circuit of the synchronous motor. So already we have seen the equivalent circuit of the synchronous generator. It is similar exactly. So if your rotor is cylindrical, the equivalent circuit looks like this. This is the simplest equivalent circuit. We are not going to study the equivalent circuit for the salient pole machines. Okay. So here the R is the resistance, armature resistance RA, and XS is your synchronous reactance, which takes into account the armature reaction effect, right? And EA is your induced EMF, VA is your supply voltage. We are giving the So this is a per phase equivalent circuit of the synchronous motor. Okay. Now the voltage equation, if you write, it is just the opposite of the synchronous generator. VA will be equal to EA plus IA RA plus J of IA XS, right? And from this I can find the expression for IA, that is VA minus EA divided by RA plus JXS. Okay. Now this is your exactly opposite manner. We can plot the phasor diagrams also, right? So here is your VA, the supply voltage, which it is taken as reference, right? This is your VA, and from BA if I'll subtract IA RA and minus of J of IA excess, then I will get ES, right? Or EA you can say. Okay, that is what it is shown. It is IARA is subtracted, then minus of J of IA excess is subtracted again. So we found EA. So it is for the lagging power factor. So for the lagging power factor, we know EA will be less than the VA, right? Okay, and the angle between VA and EA is delta, which we call it power angle or the torque angle. Sometimes also it is known as rotor angle, right? Okay, so this is a phasor diagram for lagging power factor. Now if we'll see for the leading power factor, this is the phasor diagram for unity power factor. You can see here, this is the phasor diagram for unity power factor. So the equation is same, it will valid for all the phasor diagrams, only the phase angle changes. This is for the unity power factor. Okay, so for unit power factor, VA is here and VA minus IARA, this will be a point, and then again by subtracting minus of J IA excess, I will find EA. Okay, so this is for unity power factor. Then we'll see this is for the leading power factor. For leading power factor, where IA is leading the VA. So VA is here and IA is leading by theta, we can say, right? So this is sometimes known as overexcited condition for the synchronous motor. And here your delta is EA versus EA and VA, delta is triangle, and VA minus IARA minus J of IXS is EA. So here we can see that EA is greater than VA. That means the generated EMF is greater than the supply voltage VA. Okay? So this is your leading power factor condition. So under this condition, your generator actually supplies reactive power to the system. Now we'll see the power relation. So as we have seen in case of synchronous generator also, synchronous generator, the power input is your TS omega S, right? So here your Pin is supply voltage current, that is 3 VIA cos theta, that is the input power, right? And of course we have an auxiliary supply to the field, which is VFIF. So therefore net input to the motor is 3 VAIA cos theta plus VFIF. Sometimes this VFIF may be neglected because it is injected into the field circuit. Again, it is also considered as loss in the field winding, the same loss VFIF, right? So therefore sometimes we can say the net input to the power input to the synchronous motor is 3 VAIA cos theta. So now we can see the power flow diagram here. So Pin is 3 VIA cos theta plus PFIF, and from where if I'll reduce the copper loss, that is 3 square RA plus VFIF. VFIF is the copper loss in the field winding, and 3 IA square RA is the copper loss in the armature winding. If it is subtracted, I will find the developed power, PD, right? And PD, from PD if I will subtract the rotational loss, I will find the output power, which is equal to TS omega S, right? That is PO. So PO is equal to PD minus PR, okay? And PD is equal to Pin minus P copper loss, okay? So that means if your resistance, if we'll neglect the resistance of the armature circuit RA, then your Pin is equal to PD under the condition when RA is approximately equal to 0. Okay, this is the condition. So this is your power flow diagram. Now and copper loss, of course we know this, PD is this, So now we can do a problem here, and I hope everybody can do this problem. P out by P in, right? So P out is how much? P out is given 10 HP, right? 10 into 746. Okay, and P in will be P out plus 70 is field winding loss, no need to consider that. Rotational loss is 230, right? So this will give me PD. Okay, so here PD is equal to P in. Okay, because RA is neglected, so PD equal to P in. So very simple. ये गलती हो गया ना. So this will be P out by P in 100. So whatever will come, it will be the answer, right? And EA, you know how to find. EA is VA minus J of IA excess. So IA you can find. Yes or no? Can you find IA? IA you can find, right? How will find IA? P in is equal to 3 VAIA cos theta. Cos theta is 0.707, it is given, right? So VA is given 230 by root 3. 230 is phase line voltage, so you can write 230 by root 3, and IA you can find from this expression. P in, you know, P in is equal to PD, P out plus 230. So this is the very simplest problem. Okay? You can find it out. So I hope everybody understood this. Huh? 90? 97? Okay, good. If it is 97 also it is good. Your efficiency is more. Okay. Okay, so so these are the power expressions for the motor. It is similar to the generator. So your PD will be 3 EAVA sin delta by XS, and TD also, just by dividing omega S, will find the developed torque in the motor. Now we'll see the effect of excitation. We know this power expression, which is equivalent to the synchronous generator, right? This power developed is equal to price of EAVA sin delta by XS. So here the assumption is that RA is neglected, almost is equal to 0. Okay. So therefore this expression will get PD, and TD of course will get the developed torque is equal to PD by omega S, right? Okay. So now the effect of excitation we'll see. So if we'll vary the excitation in a synchronous motor, what will happen? So let us say a synchronous motor is there, which is connected to the infinite bus. Okay, so infinite bus means, you know, the voltage is constant, the frequency is constant, right? So when it is connected, the terminal voltage of the synchronous motor will be constant as it is connected to the infinite bus, right? Now, what will happen if we'll change the excitation of the motor? Let us say it is operating at unity power factor. Okay, first normal condition, where you can say normal excitation. Yes. ये सब कहाँ थे तुम लोग? हैं? पूरा ग्रुप में आ गए. So this under normal excitation, what it means is that VA is equal to EA. That means the excitation is adjusted in such a way that the generated EMF EA is becoming equal to VA. So under that condition, what will be the IA? Can anybody tell? What will be IA? Zero, right? Very good. So IA will be 0. So there will be no current flowing from motor to the grid or from the grid to the motor, right? So therefore IA is 0 here under normal operating condition, right? And therefore we can see here IA equal to 0. Now let us say that I adjusted the excitation in such a way, that means I am varying the field current. So now I adjusted in such a way that your EA becomes greater than VA. Okay? What is EA is greater than VA, right? Okay? So what will happen then under this condition? If EA is greater than VA, then what will happen? So therefore your IA will flow from motor to the grid. Now what will be the direction of IA? The direction is from motor to grid, but what will be the angle? What angle it will make with, as it is shown in the figure, it is making an angle of 90 degree to VA, right? So how it will be 90 degree leading? How it will be 90 degree leading? If we will write the equation, your IA is equal to, your equation will be VA minus EA by J of XS, right? Okay. This is the equation. Now from this equation, we can find it out that IA will be leading to VA. VA is, let us say VA is the reference voltage, right? And we are considering here only magnitude of VA and EA. So now your IA will be, what will happen to, so your EA is greater than VA, so therefore I can write minus of EA minus VA J of XS, right? So that I can write it as IA will be equal to EA minus VA by J of EA minus VA into divided by XS, right? Okay. So now from this expression it is clear that your current will be 90 degree leading to VA, right? Because J term is here, so therefore it will make an angle of 90 degree leading to VA, right? Similarly, you can find the expression of current when your EA is less than VA. Okay. So which is shown in the next figure, right? In this figure, where you will find where EA is less than VA. Now for this case, your current IA will be lagging VA by 90 degree. So your expression here, it will become minus of J VA minus EA divided by XS. Okay? Clear? So I hope everybody understood this. So now by adjusting the excitation, that means the field current in the motor, we can change the direction of current. So under this condition where EA is greater than VA, the motor is acting as under overexcitation, right? So the current is leading the voltage, overexcitation. That means the motor will act as a condenser, or we can say the capacitance. Okay. So therefore it is giving the reactive power to the grid. How it is giving reactive power? Now we can write the expression for the power. So what will be the power expression for this? Can anybody tell? Let us write S. So what will be the expression for power here? Huh? VA? EAI. Huh? It will be thrice of VAI, right? Okay. A is equal to 3A, 3 thrice of VAI, right? This is apparent power. Now if we'll substitute IA here, so it will be J of thrice of VA into EA minus VA by XS, right? Okay. So that clearly indicates that this power is being fed to the grid. Okay. That is, this is J term is there, therefore it is only reactive component, there is no real component at all, there is no real power. Okay. So therefore only reactive power is being fed to the grid. Similarly for EA less than VA, we can find the power expression, that is also reactive power, but that is being drawn by the motor from the grid. Okay. So therefore, during underexcitation condition, your motor, synchronous motor, is drawing reactive power from the grid, and under overexcitation condition, it is supplying reactive power to the grid. Okay. So therefore, most of the time, this motor under no load condition is used for power factor correction or power factor compensation. We will see this in the next slide. Here, for power factor correction, this is used very prominently. Many industrial units they use, but nowadays it is not being used after the invention of thyristorized capacitors, right? So this synchronous motor, we can see here, if this is under overexcitation, it is providing SPM minus J of QM, right? Now the net power will be PL plus PM, PL plus PM plus J of QL minus QL. So what you are seeing here, this is the load, and this is a three-phase bus where the load is connected. Now in order to compensate the load power factor, if the load is having much more inductive power factor, in order to compensate, if we are connecting this synchronous motor, now your net power will become PL plus PM, that is the net real power drawn from the grid, and QL minus QM is your net reactive power drawn from the grid. Now as compared to this, the power factor will be enhanced when the synchronous motor is connected to the grid in parallel with the load, right? So that means your cos theta without synchronous motor will be PL by PL square plus QL square, right? Now under, if it is, let us say, ST, which is equal to PT plus JQT, so your cos theta will be equal to PT by PT square plus QT square. Okay. So we know QT will reduce somehow because QL will be greater than QT. Now your cos theta will accordingly it will improve, right? So in order to demonstrate this, we can do this problem. So this problem is just to see that how the power factor improvement we can achieve, right? So suppose there is a manufacturing plant which uses 100 kVA at 0.6 power factor lagging. 0.6 power factor means it is very less, right? So under normal operating condition, so a synchronous motor is added to the system to improve the overall power factor. So the power required by the synchronous motor is 10 kilowatt. Okay. Determine the overall power factor when the synchronous motor operates at 0.5 power factor leading. Under this condition, when the synchronous motor is operating at 0.5 power factor leading, under that condition, what will be the overall power factor of the system? And what must be the power factor of the motor to improve the overall power factor to 0.9 lagging? Okay, when the power factor is 0.9 lag, we want a overall power factor of 0.9 lagging. So for that, what should be the power factor of the motor? Can you find it? Please try to do it, or else I will tell you. Okay, got it? So इसका real power, reactive power कितना होगा? What will be the real power? 100 into 0.6, 60 kilowatt. And reactive power 80 क्या है? Unit क्या है? AVAR. Okay, ठीक है. Now we go to the synchronous motor. Synchronous motor is drawing a power of 10 kilowatt. Okay, 10 kilowatt, and it is operating at power factor of 0.5 leading. Okay, so then power factor is 0.5 leading. Now can we find Q from here? What will be the QM? QM कितना है? 10 kV. 10 kVR. 10 kVR किसका? How will find QM? Cos theta is how much? PM by PM square plus QM square square root. Okay, so from this you can find QM. Yes or no? So what will be the QM? Can anybody tell? This is equal to 0.5. PM you know, PM is 10 kilowatt. Okay, now what will be QM? 17.82 kVA. Okay, now you can find net total power. Real power is 10 plus 60. It is 70 kilowatt, and total reactive power is 80 minus 17.32. How much it is? 80 minus 17.32. QL minus QM. How much? 62.68. Now you can find improved power factor. So then you find it PT by PT square plus UT square square. Okay, how much you got? कितना है? 0.82. So everybody getting this 0.82? Everybody got 0.82? Then second part you do yourself. 0.8. Second part can you do? What must be the power factor of the motor to improve the overall power factor to 0.9 lagging? So this is also 0.82 lagging. Okay. Now we need to find the power factor of the motor so that your power factor will be improved to 0.9. Can you do this?